I want to talk today about mass spectroscopy, or how it's sometimes abbreviated as MS, or alternatively mass spec. And it's a method of determining the size of the molecule and getting a sense of the molecular weight. The way this is usually done is we have a sample and we want to convert it into ions. So we do something to it. In this case, we hit it with an electron beam to actually knock electrons out of it. And what we get are a bunch of ions. And what we really care about is the M/Z ratio. That's the mass to charge ratio. Ideally, we want Z to be equal to 1. If Z is equal to 1, then the M to Z ratio ends up being our mass. So these differently charged fragments fly up towards a magnet, and the heavier ones are deflected less by the magnet. The smaller ones are deflected more by the magnet. And when they hit the detector, they hit at different places and different times, depending on how your detector works. And you can get a list and a print of the different ions, fragments that form. And as I said, the goal ideally is to have a charge of 1, so your fragments, M/Z, tell you the mass of the fragments. Ideally, we don't want the molecule to fall apart, but a lot of times when you're blasting something with an electron beam, it does fall apart. For example, this is a mass spec of 2,4-dimethylpentane. Ideally, we want a big peak at 100 because that's the molecular weight of 2,4-dimethylpentane. Unfortunately, when we blast the molecule with whatever we blast it with, it breaks apart into a whole bunch of pieces because once you hit it with electrons, it's not stable anymore. So we get all kinds of small pieces. For instance, we get peak 15 smaller than the mass because we lost a methyl. We get 43 smaller than the mass because we lost an isopropyl, and so on. Now, really talented, really experienced people who do a lot of mass spec will be able to tell you what each of these fragments mean, and they can tell a lot about a molecule based on the mass spec. We're going to, this semester, focus on the basics. And we'll look at a few examples of that in a minute, but I want to focus first right now on a couple of definitions. First, the biggest peak in the whole mass spec is called the base peak. So that's the biggest in terms of abundance. We got the most of that ion, or 41, so it's called the base peak. It's set to be 100%. The peak corresponding to the molecular ion, the ion representing our entire molecule, is called the molecular ion, or the M+ peak, because it's positively charged. Let's look at an example of the mass spec of hexane, and you can see we have our M+ peak at 86. And then we have the minus methyl, minus 15, minus ethyl, minus 2 CH2s and a CH3, and so on. We can see each of these carbons being chopped off, giving us smaller and smaller pieces as it falls apart. Now, for us, the most important one is this M+ peak because it tells us the molecular weight of our sample. You also notice a very small M+1 peak just above the 86. That's because we have different isotopes mixed in with our molecule. Most of our carbons are carbon 12s, most of our hydrogens are H1s, but we've got a few H2s, deuteriums every once in a while. We've got a few carbon 13s every once in a while, and that gives us a little bit of something that's not 86, but 87. We call that the M+1 peak. On the isotopes and the elements in your sample, the M+1 peaks could be really small, they could be pretty big. For instance, if you're looking just at carbons and hydrogens, almost all of the carbon and hydrogen are the major abundance isotopes. Very little bit of carbon-13, almost no naturally occurring deuterium. If you look at, however, chlorine, about 75% of it is the chlorine-35, and about 24% or 25% of it is M+2. So that's a pretty substantial amount. And what it means is when you have a chlorine, you'll have a peak at one position, and then two bigger, you'll have another peak about 1/4 the size or 1/3 the size, 3-to-1 ratio. Bromine, it's even more dramatic. 79 for bromine 79 is 50%, bromine 81 is 49%. Again, it's M+ and M+2, so you'll see a pair of peaks. These are really key indications that you have a chlorine or a bromine in your molecule. And let's look at some examples of that. Notice that the M+ peak, the molecular ion, is 122. We've got a very small M+1 peak, and then we've got an M+2 peak at about the same size. What that means is it's strongly suggesting we have a bromine. When M and M+2 are the same size, that means bromine. So when I see the M+ and the M+2 in a 1-to-1 ratio, that tells me my molecule has bromine. Alternatively, in this molecule, we see the M+ at 78. We have a small M+1, and then we have an M+2. And the M+1 to M+2 is about, M+ to M+2 is about a 3-to-1 ratio. That tells me chlorine. So that's what I'm looking for. Now, I will make it clear on all of these samples that you have to analyze this semester that they're in about a 3-to-1 ratio. I'm not going to have you guessing and measuring with a ruler to say, is this 3-to-1 or is it less? I want it to be clear to you, so I will make sure it's clear. Couple of things to remember. I've got a list here of things to look for in your mass spec. M to M+2 ratio of 1-to-1 is bromine. M to M+2 3-to-1 is chlorine. A little bit harder to detect, and we're not going to focus too much on this semester. Sulfur actually has an M to M+2 of about 25. Important thing to notice is if we look at the M+ peaks for all of these samples, this was 122. I go to the previous one that we looked at. It was 86. The one before that is, 100. What you'll notice is all of these numbers are even numbers. And it turns out that there's only one time with the kind of mass spec we're doing and looking at that you're not going to have an even mass. So what I've done here is I've looked up the mass spec of diethylamine, and you can see that the mass of the molecular ion is 73. It's an odd number. And that's actually the only time we're going to have in the mass specs that we look at an odd number for the molecular ion, is when we have an odd number of nitrogens. And that's really useful for identifying nitrogens in our molecule. An odd mass equals odd number of nitrogens in the molecule. Now you might say, if I have an even mass, does that mean I have 2 nitrogens? Well, it could, but I'm not going to have you focus on problems like that this semester when we're learning how to do mass spec. We're going to keep it simple. So these are the most important things that I want you to look at when we're first learning how to do mass spec. The mass of the molecular ion, the signal that indicates bromine, chlorine, the odd mass for nitrogens. Turns out that if iodine falls off really easily, it gives a M-127 peak. We're not going to focus on that as much, but that's something to be aware of. There are a couple of common fragments that you will focus on more as we learn, but these are the things I want you to focus on first. I'll look at how we're going to use the new techniques we've learned to analyze this compound. I've got the Nmr, IR, mass spec, and C13. I'm going to start by looking at the IR. I always just check the IR real quickly to see if there are any obvious functional groups there. So let me open that. And I look at this, and I don't see any obvious functional groups. I definitely don't have an OH. I don't have a C double bond O or a C double bond C, C double bond C, C double bond O. I don't see any signs of an ester or an amine. So right now, this mass spec, this IR tells me I don't have a lot of those kinds of functional groups, which is important in eliminating things. Go to the C13 next. And what I noticed in my C13 is I have 1, 2, 3, 4, 5 types of carbons, which is really useful and helpful. So I'll make a note of this. So I've eliminated all of these functional groups. I know I have 5 types of carbon. I think next I'm going to look at the Proton Nmr. This Proton Nmr, the first thing I look at is this peak right here, between 3 and 4. There are only certain types of hydrogens that show up between 3 and 4. 2 most likely possibilities are a hydrogen on a carbon next to an oxygen, or a hydrogen on a carbon next to a halogen like bromine or chlorine. I know that it's not this where the R is an H because I know I don't have an alcohol from the IR. So it's either an ether or a halo compound. And I have ways of testing that, and I'll look at both of those later. Right now I want to focus more on that signal. In particular, I want you to notice that it's split into a triplet. What does it being split into a triplet mean? It means it has 2 neighbors. This is my H, the H that gave me the signal. Since it's split into a triplet, it has 1, 2 neighbors. I only look at the very next door carbon, and I'm guessing that there's no hydrogens on the other side. So it looks like that. Well, how many hydrogens are here giving me the signal? I've got two neighbors, 1, 2, but how many hydrogens give me that signal? I can tell that from the integration. And if I look at the ratio, 0.25 to 0.25 to 0.5 to 0.38, that looks to me like 1 to 1 to 2 to 1.3, which doesn't make a lot of sense. So we probably have to multiply everything to get a whole number. When you measure everything out and divide, it actually comes out to be 1 to 1 to 2 to 1.5. 1 to 1 to 2 to 1.5. Well, 1.5 doesn't make sense, so we're going to double everything, and we're going to get 2 to 2 to 4 to 3. And so that tells me that there are 2 hydrogens giving me that signal. So I've got 2 hydrogens next to 2. A fragment like this with 2 hydrogens next to 2 hydrogens. And I got all of that from my 1 NMR signal. Keep in mind I have 5 carbons, so I've assigned almost half the carbons. Now, let's look at our NMR. This signal right here below 1, there's only one thing that gives a signal below 1. That's a CH3 not near electronegative atoms. So now I've got a CH3 in my molecule, and I actually have 2 ends of my molecule if I think about it. I'll try to draw it like this. So on one end of my molecule I have a CH3 that's not near anything electronegative, and then on the other end of my molecule I have this fragment, CH3 something CH2 CH2X. Well, I know that I have 5 carbons total. I've assigned 3 of them, so I only get 2 carbons left. There are only so many ways you can arrange those extra 2 carbons, and I always suggest you guess and start with the simplest one and see if that makes sense. So I'm going to guess and say that those extra C's that I haven't assigned yet are 2 CH2s. Let's go see if that makes sense. Well, if we look at this, what you'll see is we've got this peak right here for, it integrates to 0.5, which we said corresponds to 4 hydrogens. 4 hydrogens very nicely fits 2 CH2s. So we've got 2 CH2s overlapping with one another. That's why it's a multiplet. So yeah, it makes a lot of sense. So it does seem like this molecule that we've written is right. We only have to figure out what X is now. That's when we're going to use the mass spec. When I look at my mass spec, I notice that the M to M plus 2 is in a 1-to-1 ratio. That clearly screams at me that I have a bromine in this molecule. So X equals Br, and this is the structure of my product, or my unknown, I should say.